All right, so welcome to another exciting episode of not AP, Advanced Level Chemistry. Advanced Level Chemistry taught at an AP level, okay? Because y'all are totally 100% capable. Hey, by the way, if they're liking these videos, what are they supposed to do?
Like, subscribe, comment.
Yeah. That's what they do. Hit that like button, ring that notification bell, subscribe to that channel. Okay, when we're looking, okay, we say that sodium and all the alkaline metals form a +1 oxidation state. Well, why? Well, if we look at sodium, to lose the first electron takes 496 kilojoules per mole. Okay, so if I had a mole, I had 23 grams of sodium, and I want to knock all those electrons off, just this electron, which electron here in sodium, which electron is the one that's going to be removed by electricity? 3s. The 3s. So it's this electron is going to go. So it's going to take, the 496. We're just going to look at relative numbers. Okay? Now, once you remove this electron, notice now there's a huge increase, 10 times almost, increase in ionization energy to remove the second. Where would the second electron have to come from? 2p, which is now on a much closer energy level. It's on the 2 versus the 3rd energy level. It's in a noble gas configuration. Remember, it would be neon plus 3s1. So once this one left, what's it left? What's it like?
Neon.
Neon. It's isoelectronic with neon. It's got 10 electrons down. Now, to try to remove this second one takes a tremendous amount of energy. That's not going to be feasible. So the alkali metals will lose 1 electron readily, but it's not going to want to lose any more because it's going to be such an increase in energy that it's not going to be feasible. Now, if you put enough energy and you can knock the electron off, but in an ordinary chemical reaction, sodium's only going to want to lose that first electron. Number 1, it takes a little bit of energy. Number 2, it has that stable noble gas configuration. That's what atoms want to have, that filled octet, the 2 and the 6, that 8 electrons. But magnesium has 2 electrons. Now, remember, sodium has 11 protons, magnesium has 12 protons. Both electrons are in the 3s. This electron's in the 3s, the same bout distance from the nucleus. But so because this has 12 protons versus 11 protons, this one's held more tightly. So it takes more energy to remove this one than it did that one. It's smaller. We say as you go left to right, it gets smaller. The more protons are pulling the electron cloud in more tightly, makes it harder to remove. Well, there's the experimental evidence that shows that. Now, to remove the second one is harder. This is the first one that's going to come out. Now, the reality is it's 50-50. Which one's going to be the first one? It doesn't matter. But the second one that comes out is a little bit harder. Now, there's 2 reasons why it's harder to remove the second one. Number 1, what's the charge going to be on magnesium once you remove 1? Positive. So you're now trying to take something negative away from something that's positive. But the more important or more, the one that has a more of an effect is, I don't know if any of y'all have an older brother or sister that's going off to college and you have to share a room, share a car, something, okay? And you try to act sad that they're leaving, but when they leave, you get your room to yourself, okay? Well, that's kind of the way this is. These are both negative. They're repelling one another. Both negatively charged. Opposite spins, but they're both negatively charged. So this one is actually helping to push this one out. So somebody's putting in energy from somewhere. Energy is coming in. But this is saying, hey, feel free to go. It's no problem, So it's actually helping to remove the first one. Now, once this first one's gone, now we don't have any of those electron-electron repulsions. So now it's just straight up having to remove the next one. So this is actually a measure of how much electron-electron repulsions there are within a sublevel, right here. But it's always harder to remove the second than it was the first. But now notice, after it loses 2, after both are gone, now where's the third one come from? The 2p again. Well, what happens? A big increase in ionization energy again, right? So magnesium is going to tend to lose 2 electrons relatively easily, form a +2 ion, but it's not going to form +3. Okay? This is why, again, we're just trying to showing, well, how, and in terms of ionization energy, why it's +1, why it's going to be +2. It's going to lose those valence electrons. So aluminum, now look at this. Here's a little bit of an anomaly in our trend. But notice that in aluminum, now the first one's coming out of a 3P. A little bit higher sublevel. There's some, when you take AP, I'll get in a little bit deeper. Normally I get this, but we're out of time for this year, so I'm skipping over the why. You just have to trust me that because it's in a higher sublevel, it's just a tad easier to remove.
Why are would it, if you get to like past argon, would it go down again?
Yeah.
So it would go back down to like.
Yeah.
Gotcha.
Just because you asked that question. I have to show you my favorite graph. They took it out of this book. The trend, here's your trend in ionization energies. So we're looking at this sodium, we're looking at this family right here. And so here's your general trend up, but you can see here's the magnesium, here's your aluminum right here. Okay, sodium, magnesium, aluminum, there's that little drop.
Yeah.
But then it goes up, but when it gets to argon, it drops way back down again because you go to the 4th energy level.
That's what I was.
Yeah. And then the same trend starts over again, but now you go into the Ds, but then the general trend is still there. I just don't have time to go into why there's these little anomalies, why there's the dips. Okay, take AP Chemistry and I'll fill you in. No, we don't have time.
You just skipped the lesson. I don't know why.
Leave you in a mystery. Okay. So back to this. So aluminum, once aluminum loses this one, then we're back to the S's, okay? But it's got 13 protons versus the 12, so it takes even more energy to remove it out of the S than it did out of these, okay? And this is, again, there's no more electron-electron repulsions there, so it increases to remove this third one because now you're getting rid of that one so you don't have the electron-electron repulsions. Plus it's now minus, now it's +2, and you're trying to take another minus away from it, so it's even harder. But notice after it loses 3, where's the 4th one got to come from? 2P, right? So this one, now we have a huge jump, again, in ionization energy. So aluminum will lose its 3 electrons, but it's not going to want to lose a 4th because of that big jump. Okay? So that's why we get those oxidation states that we get. That's why the alkaline metals will lose 1 easily. The alkaline earth metals will lose 2, but they're not going to lose 3 because it's so much harder once you get that noble gas configuration. So this one is neon and 3s2. This one is neon plus 3s2, 3p1. So once these go, it's isoelectronic with neon. Once these go, it's isoelectronic with neon. Once that goes, it's isoelectronic with neon. Okay? Now what do you think that means about the size then though? If these all 3, once we have Na plus, we have Mg2 plus, and we have Al3 plus. They all have 10 electrons, right? Are they all going to be the same size?
No.
Why not?
Energy.
They have different amount of proteins.
Different numbers of protons.
Yeah, what she said.
So which one's going to be smaller?
That one.
Okay? The more protons, the more that electron column is going to get pulled in more tightly, right? So it's going to get smaller. So the last thing that we're going to look at is the size of ions. Okay. So here's our trend that we saw in the size of atoms. Okay? But again, if I'm going to make sodium an ion, I'm going to lose that third energy level, right? So what do you expect to happen to the size? Get bigger or smaller? Smaller. So when you look here, you can see here's the lithium atom, here's the lithium ion. Significantly smaller. Sodium atom, sodium ion. Okay? So this is, I want you to write this down right underneath where it's oxidation states, where you have the notes on oxidation state. Okay? Our God's giving me the look. God, I gotta open up my Chromebook. God, I gotta do something. Oh. God, Mr. Hobbs making me work. It's 7th period on a Tuesday. That's defined as free day, isn't it? It's okay, you don't take notes anyway. Okay, this is what you're going to write. Cations, okay? Cations, and don't write anything else, just write that word. But do we all know it? Hey, where's this bag? Where's his bag?
Oh, and everything I have for over here.
Okay, give him his bag. Okay?
I say do it with my foot.
Yeah.
About the new book.
You're gonna have a million views now because I'm on.
Okay,
Yeah.
here we go. Yeah. I just want to make sure, what are cations? Positive ions. So make sure you know that cations are right up there, but they're positive ions. So just so when I say cations, we know they're positive ions. Okay, so Ace, we're going to write all this down. Okay, cations are significantly smaller than the atoms from which they came. The atoms from which they came. Because cations are significantly smaller than the atoms from which they came, because
The electrons are different.
He's losing an energy level.
okay. What's your answer again?
I said,
No. What she said. Okay.
Yeah.
Because the ions have lost their valence shell. The ions have lost their valence shell.
But is that not only with one on the outside? Like
No, magnesium's lost its both of them out of the 3s. Aluminum's lost all three, the P and the 3s. You lose the entire valence shell. So it makes the cations are always going to be significantly smaller. So what does that mean about anions?
They're going to be significantly bigger.
Okay? So if we go and we look at anions, okay, and compare this way, okay? If we compare this way, now again, if we want to compare the same thing, okay? So F minus, this is 1s2, 2s2, 2p5, but if it's F minus, what does that mean it's done with electrons? Right, okay? You're over there for a reason. Okay? Come on. Now, if you guys are trying to communicate back and forth, you need to close your Chromebook. Okay?
You just took the
Okay, I know.
access of it.
Okay? Here we go. All right? Now, if I'm going to gain, if I have an F minus, what does that mean in terms of electrons?
You're gaining electrons.
I'm gaining, so it's really, now it's going to be 2p6. So what's that going to be the same as?
The next one on the thing.
Which is neon. So F minus is going to be the same as, so the F minus is the same as neon. Well, what about O2 minus?
Same thing.
Same thing. What about if it's N3 minus here?
Same thing.
Okay? Now it's going to be 1s2, 2s2, 2p3, but it's going to gain 3, so it's going to be p6. So they're going to have 10, right? But This is going to have 7 protons. This has 8. This has 9. So if I was going to compare sodium, magnesium, aluminum, nitrogen, oxygen, and fluorine, and even neon, how many electrons does each one of those have? 10.